Hello again. Today I will say something about stability of the phase portrait. I mean, we will be speaking about similar case like in the previous video, but this time I will show you how looks like the stability of the solution depends on the values of the linearized parameters of the system. I mean, today it's a topic, it's a stability of phase portraits. Okay, and last time we stated that the equivalent linearized solution in the phase coordinates is as follows. I mean the v tilde over dx tilde equals minus equivalent omega 0 squared times x tilde minus 2 equivalent damping coefficient times v tilde, and also we figure out that the solution in time will be given by such an formula R1t plus C2e plus 2RT, and it causes that the velocity will be as follows. I mean, it will be C1 times R1e plus R1t plus C2e R2e R2t with plus. But from our point of view, it doesn't matter because there will be some values of the R1 and R2. Okay, and last time also we rearranged our equation to the matrix form, and we stated that the filling of the transformation matrix will be in that form, and also there will be some vector which is given on the Cartesian plane. I mean, it's a parameterized curve on the Cartesian plane. I mean, here we have the situation that one curve, some curve is transformed by some affine transformation to our phase portrait. Okay, and we consider that if the equivalent omega square is smaller than 0, last time we stated that R1 will be smaller than 0, R2 will be bigger than 0, or R1 will be bigger than 0, R2 will be smaller than 0, and we stated that the result of that assumption will be as follows, that y can be computed as some function, some generalized hyperbolic function where it will be give me the second because I have to check it, R1 will be here. It means that it will be R1 R2 over R1. Okay, and we stated that such a curve approximately will look like the hyperbolic function, or maybe sometimes it will be something like that. Okay, by the red color I will show a different form. Okay, I mean we have something with the instability, I mean with the singular point exactly at 0. Okay, the second thing which we considered was for the situation when the equivalent omega will be exactly 0, and we stated that then we have the situation where give me the second, I need, wait, I will write down the values of the roots of the characteristic polynomial, and here we have the h equivalent square minus omega equivalent squared, and we see in that case the one root, let's say first root will be R1 and the second root will be minus 2h equivalent h, and we stated that in that situation, for that case, we will have the equation where the x is, let's say, 1 or y will be, let's say, 1. I mean, we have or. Depends on the situation, because the second condition is that R2 will be, in that case, it will be minus 2 equivalent H and R1 and R2 will be 0. And we stated that depends on the situation, we are able to find such a solution or such a solution. And it means that on the phase plane we have such an image. I mean the straight lines. Okay? Also, there was the second condition. I mean, if the equivalent omega square is bigger than 0, and also we have the case of the over-damped system, I mean where the h, equivalent h square is bigger than omega or equal, no, bigger of equivalent omega, then we stated that as a solution we have almost exactly that thing, but it will be expressed by the x to the R2 over R1. I mean, this time we have something which will be called node, because it will be some kind of the generalized polynomial function. It will be for the odd values as a power, and for the even values we can consider also such an curves. Okay, and of course here we have it's xy, xy, and xy in our case, because it's from the Cartesian plane. Okay, and also we have the situation where there will be our system will be overdamped. Sorry, it will be underdamped. I mean, when the damping is smaller than, let's say, vibration in the system. I mean, the elastic part. I mean, where the equivalent omega square is bigger than 0, but we have the situation where equivalent omega is also bigger than h squared. I mean, when the value from the square root is smaller than 0. It means that we will have the imaginary numbers as the complex number as R1, R2. And we remember from the previous videos, from the videos about the free vibration of the single degree of freedom system, that in such a situation we can express the solution as such a thing, plus, minus, and it will be omega 0 equivalent, omega equivalent square minus 2 equivalent square times imaginary unit, and the same situation here. And then the solution has a little bit different form, okay? Because even if you will use that thing, and if you will put the complex number, then we are able to rearrange our equation to such a form. I mean, to the form of the E times E minus 2 minus equivalent HT times some constant times, let's say, sine omega h t plus some phase shift. Okay, and in that case, then the velocity, it will be first derivative of such a thing, of that formula. And it means that as a result we will get that it will be minus 2h times e to the power of h, equivalent h times t plus times d times sine omega h t plus phi, and it's a derivative of the first component, and plus the derivative of the second component. Equivalent h times t times d, and we have to compute that thing. It will be omega h times cosine omega h t plus phi. Okay, and we see that again we're able to express the phase portrait as a such a thing. I mean, it will be the constant factor in the form of the e minus, I mean the exponent of minus h equivalent h t, because it's a common factor of the every single expression, minus a equivalent h t plus some affine matrix as a transformation, and there will be the vector which is composed of the sine omega h t plus phi. Oh, sorry, it's not especially readable. And from the other point, we have the cosine as a second element, omega h t plus phi. And what we have as a filling of that matrix? We have that here we have the d0, because in the first equation we don't have any cosine component. And from the other hand, we have the minus equivalent h d plus, sorry, of course not plus, it's last component of our matrix, d omega h. And we know that such a curve, it's a equation of circle. I mean, it's an equation which show us in the parameterized form, which show us the circle and the face and the Cartesian plane. It's easy to show it because if we put that x, it's that function sine omega h t plus phi, that thing it's a cosine omega h t, sorry, omega h t plus phi. And if we will take the squares of the both sides we have, and we'll add the both equations, we'll get that the x squared plus y squared is exactly equal 1. Oh, I forgot about the parentheses. I will show it by the red color to emphasize that mistake. Okay, and we see that it's an equation of the circle. It means that on the Cartesian plane, the circle will be visible, and due to that affine transformation, we will see on the face plane, I mean the x, v, okay, because on the Cartesian plane, I mean the x, y, we will see the circle. If we are talking about our face portrait, we see that it will be, that it will be the circle which will be scaled and rotate and maybe sheared a little bit, and also we have some factor which makes that the radius of that circle will increase or decrease, depends on the situation. Okay, I mean, as a face portrait, we are supposing that it will be the spiral due to that component which makes that the radius will be higher and higher, or smaller and smaller, or lower and lower. Okay, here we have such a face portrait. Only for the h0 we will get that there will be the ellipse, such a thing, let's say x dot v dot. Okay, and the last interesting case for us, it will be the case where the equivalent omega square is bigger than 0, but also equivalent omega square is exactly the same as h square. What does it mean? It means that as a solution we get exactly the same roots. I mean, the R1 will be exactly the same as R2. And it means that from our equation of that case, I mean, from that equation or from that equation, we will have the same number as a power of that thing. And it means that y will be exactly equals x. It means that on the Cartesian plane, we will have the straight line. After the scaling, rotating, and shearing, we will get as a face portrait such and such a thing. I mean, it will be X tilde V tilde, it will be the bunch of the lines, something like that. Okay, and if we'll put together all that phase portraits, we can draw something which is called stability diagram, and it's given by the equivalent omega square and equivalent damping. And due to our consideration, we know that for the negative omega equivalent square, we have the saddle points. It will be such a thing, and it's an unstable system. Then, I mean, saddle point. Second thing, oh sorry, my bad. Saddle. And for the omega 0 square, we have the lines in that way. Here we have the unstable lines. Here we have the stable lines. Here we have some boundary given by that condition. I mean, where the equivalent H is exactly equal to equivalent omega because of our last condition, and exactly at that line we have the stars as a solution. Here we have unstable star. Here we have stable star, and here we have the spirals, unstable spiral, stable spiral, and here we have the nodes. I mean, here we have that portrait which is given by that polynomial functions. Let's say it will be in that way. Unstable node, of course here we have such an rotation, here we have rotation to the process is stable, I mean goes to 0 to the center point. Here we have the arrowheads in that way, here we have arrowheads outside, and here we have stable nodes. And it looks exactly like that, but the arrowheads have different facing. I mean, to the critical point. Okay, as you see, it is the stability diagram. I mean, it is our, let's say, solution and the way how the system will behave due to the equivalent linearized system parameters. Thank you for your attention. See you next time on the other movie.